Welcome to the Deep Dive. This is where we take sources you send us, could be articles, videos, anything really, and, well, we dig in.
Yeah, we pull out the really important bits, the interesting stuff, hopefully giving you those aha moments without, drowning you in details.
Exactly. And this time we're looking at a transcript from a YouTube video. It's pretty technical. It actually shows someone modifying a PLC project.
Right, on an OKUMA OSP-P100 CNC machine. So, our mission today is figuring out how someone can take existing hardware outputs on one of these machines and basically repurpose them.
Repurpose them using the machine's own internal software.
Precisely.
Yeah.
Using this embedded software called D300win to change what the machine does.
Okay, so let's set the scene. What was the actual problem the user was trying to solve?
Well, they needed the CNC machine itself to trigger an external relay. This relay was supposed to send a signal to a separate measuring device, a sourcing measurement device specifically.
Okay, trigger a relay. Sounds simple enough, but I sense a catch.
There definitely was. The CNC machine uses what's called a syncing circuit for its outputs. Think of it like this. The signal is referenced to the 24-volt power supply, and it actually delivers 0 volts to signal on.
Ah, okay. And the measurement device?
That used a sourcing circuit, completely different electrical language. So syncing and sourcing, they just don't talk to each other directly. Incompatible.
Gotcha. Different dialects, electrically speaking.
Yeah.
So how did they try to bridge this gap? What outputs did they look at first?
So the first one they considered was an output labeled YB37. The video links this to something called OSPS1, a digital output.
And these things have, like, super specific addresses, right?
Yeah, very specific. Like the transcript mentioned 007.06, bit 6, channel 1, MSC ID 3, address 4 of a DC module. I mean, it's deep in the machine's architecture.
Wow.
But importantly, the PLC, the machine's brain, already had a name for this physical output. It was globally declared as SPS1 with the logical address QX624.00.
Okay, so it exists physically, and the software knows about it. So why not just use it? They tried linking it to a function, M41.
They did. M41 is normally for spindle gear changes. The idea was, okay, maybe we can just trigger this output when M41 is called.
Right.
But the machine threw an alarm. Turns out this specific machine didn't actually have the optional gear change hardware or software enabled.
So the physical output wire was there, connected maybe, but the logic for M41 to control it wasn't active because they hadn't bought that specific option.
Exactly that. It really highlights something important. Just because the physical part is present doesn't mean the controlling software logic is automatically usable. You often need the specific machine option enabled too.
That's a key point. Physical presence isn't enough. So that was a dead end. Did they look anywhere else?
They did. They explored another potential output, this one related to something called OCLP, physical address 0, bit 5, or IB5.
Was that one usable?
Well, kind of similar story, but slightly different. The physical output existed. It was even wired up to the output module. But the problem this time was it wasn't digitally connected to its logical counterpart, OCLP, within the PLC's network system, the device net.
So, physically there again, but like digitally isolated, not talking to the right part of the software.
You got it. Physically present, logically disconnected for that specific communication path.
Okay, so after hitting those walls with M41 and OCLP, what was the solution? They went back to the first one.
Yeah, they circled back to that OSPS1 output, the YB37 one. They confirmed it was physically functional. It could be turned on and off if commanded correctly.
So the new plan became, how do we command it using different logic?
Exactly. The goal shifted. They decided to trigger this OSPS1 output in parallel with the existing logic for M58 and M59.
M58 and M59, what were those doing?
Those M codes were already part of a custom system they were using. It was for measuring the eccentricity, like how off-center a tube was before the machine started cutting it.
Oh, okay. So repurposing an unused output by linking it to an existing custom function. Clever.
Very. It's about working with what you've got. And that M58, M59 logic was already quite involved.
That's so.
Well, M59 would turn off the sensor signal, set a limit on the spindle speed, and then position the spindle very precisely using M19.
Okay.
Then M58 would trigger the sensor, wait a bit, rotate the spindle, and then wait for a signal back from the sensor to check if the tube was centered properly.
Right, so it's a whole little sequence.
Yeah.
And they wanted their extra output to just turn on with M58 and off with M59 alongside whatever else M58, M59 were doing.
That was the plan. Add the OSPS1 activation into that existing sequence.
Okay, now the really interesting part. How did they actually do this in the software? that D300win system.
Right. This is where you get into the nitty-gritty of the PLC programming. First step, find the right place in the code.
Like finding the right file or function.
Exactly. They needed the logic block, the POU, that handled M58, M59. The video mentioned it was POU CHK1042 inside a worksheet called CHK121, specifically block 21.
Sounds like navigating a maze.
It can be. Think of it as finding the exact room in the machine's control blueprint where that specific process happens.
Okay, they found the room. What next?
They needed to find where their target output, OSPS1, was originally defined as global declaration. This was likely in an initialization module.
The master list of outputs? Sort of.
Kind of, yeah. They found it, and then they copied the local variable associated with it, which helpfully had the same name, OSPS1.
Copied the variable name, okay? And then,
and this is the crucial bit, they went back to the module handling M58, M59, that 0Z042 module. They opened its local variable declaration table.
the list of variables known only within that room.
Precisely. And they pasted the copied OSPS1 variable right into that local list.
Why is that simple paste so important? What does it actually do?
It creates the link. Think of the global variable like the main phone number for that output. Everyone in the system knows it. By declaring OSPS1 locally inside the M58, M59 module, you're essentially saying, hey, this specific module now has a direct line to that main number.
Ah, okay. It makes that global output accessible directly from within that specific piece of code.
Exactly. It lets the logic in that module directly control or dial that output. It creates that dedicated pathway. And just a side note, the video mentioned address 007.06 earlier, but the software screenshots seem to show 00.1 for OSPS1. Probably just a slip of the tongue in the video. The software mapping is what counts here.
Good clarification. So the connection is made locally. Now they need to add the actual switch.
Right. Inside that M58, M59 logic block, CHK1042, they created a new coil. That's like a software version of an electrical relay or switch, something you can turn on or off with code.
Okay.
They then searched for the OSPS1 variable, and because they just declared it locally, it now showed up as available to use right there. They selected it for their new coil.
Makes sense. And they labeled it.
Yes, very important for maintenance later. They added a comment, spindle gear spare 1 linked to YB37, just makes it clear what this new switch is doing.
Good practice. And the final connection.
They wired this new OSPS1 coil in parallel with the existing logic for another output called OHLP. What's that? That's the output that normally controls the machine's main work lamp. But interestingly, just like the M41 gear change, using OHLP directly often requires buying another specific option.
So they couldn't use the lamp output directly for their relay either, but they could tap into the signal that turns the lamp logic on and off.
Exactly. They piggybacked onto the lamp's activation signal within the M58, M59 logic to also trigger their desired OSPS1 output. Very resourceful.
Okay, the code is modified. Now for the real test.
Yeah.
Putting it on the actual machine. What did that involve?
First, connecting the PC to the CNC machine, going online, then compiling the modified PLC project.
Compiling, like checking it for errors.
Yeah, basically turning the human-readable logic into code the machine understands and checking for mistakes. Good news was it compiled with 0 errors.
Phew. Any warnings, though?
Yes. During debugging, they got an overlap warning. That's pretty standard, though. It just means the program on the PC is different from the one currently running in the CNC. A safety check, really.
Makes sense. So then they download it.
Yep. They downloaded the modified project, full project, and the source code from the PC to the CNC. The video mentioned this creates a good project backup on the machine.
A safety net in case the changes cause problems.
Yeah.
Smart.
Very smart. You want a way to revert if things go sideways.
So they downloaded it, rebooted the machine, and did it work?
Not quite immediately. The first time it rebooted, the machine actually displayed an error. Illegal modification of PLC.
Whoa! Like the machine knew it had been tampered with.
Exactly. It's a built-in security feature to prevent unauthorized or potentially dangerous changes to the core controls.
Okay, that must have been a tense moment. What happened then?
Thankfully, according to the transcript, a second reboot did the trick. The error message went away, and the PLC started up normally with the new code.
Persistence pays off.
Mm-hmm.
And the result? Did the output trigger?
It did. When they ran M58, both the OHLP logic for the lamp and their new OSPS1 output turned on together. And when they ran M59, both turned off. Success.
Brilliant. But wait. If the lamp logic was also triggering, did that affect the actual machine lamp?
Ah, yes, good point. Initially, it did. The new logic essentially took over control of the lamp signal overriding the normal operator panel button for the lamp.
Okay, so one small snag. They needed the output triggered, but they probably still wanted the operator to be able to tune the lamp on and off manually, right?
Precisely. So there was one more refinement needed.
How do they fix that?
They had to go back into the software. This time, the video mentioned going into the local variable declaration in a worksheet called 0R It seems they might have initially added the OSPS1 declaration in more than one place, or perhaps this was a different context.
Okay.
And in that specific worksheet's local variable list, they deleted the OSPS1 declaration they had added.
Interesting. So removing the local link in one specific area, perhaps the main runtime area, but keeping it in the M58, M59 module.
That seems to be the idea, yeah. Untangling the lamp control from their specific modification. Then they compiled again.
So getting that not congruent warning, maybe.
Potentially, yes, if the online version hadn't caught up yet. And then another download project and source back to the CNC.
It sounds like a careful process of tweaking and testing.
It really is. You make a change, you test, you observe all the effects, you refine. And finally,
The final test.
success. After that last adjustment and download, M59 turned off their custom OSPS1 output, M58 turned it on, and the machine lamp now worked independently from its own control panel again.
Perfect. They got their custom signal working without messing up the standard lamp function.
Exactly. Problem solved.
So let's just recap the big win here. They managed to take a physical output, OSPS1, which was wired up but not used because its intended function, M41 for gear changing, needed a paid software option.
Right, an option they didn't have.
And they successfully repurposed it. They made it trigger based on different M codes, M58 and M59, which were already running their custom tube measurement cycle.
And the way they found that output was key too, wasn't it? By looking at the manuals and diagrams for functions associated with optional features like the M40, M41 spindle gears.
Because those outputs might be physically present but logically dormant if the option isn't active. That's a really insightful approach.
It is. It's thinking about the hardware lifecycle manufacturers might install common hardware across models but enable features through software.
So even though the M41 output was wired, its intended logic was locked. The workaround was tapping into its physical activation using a different trigger. They already controlled the M58, M59 logic.
And the final confirmation was seeing that physical output, OSPS1, click on and off exactly when M58 and M59 were executed in their program.
Fantastic. So summing up this whole deep dive, it's a case study in creatively modifying PLC logic, identifying available hardware, digging into the existing software structure,
making those careful parallel additions, linking variables correctly between global and local scopes,
and then rigorously testing and refining through online connection and multiple downloads until it works just right, all to achieve a custom goal without buying extra options.
The real aha moment here, I think, is just how much control and flexibility can be hidden within these complex systems if you know where and how to look.
It shows you can sometimes work around limitations by delving into that PLC software, really customizing the machine's behavior.
Absolutely. It's empowering in a way.
Which leaves us with a final thought for you, the listener. If a complex piece of industrial machinery like this has these kinds of, well, hidden or repurposable capabilities waiting to be unlocked,
what other complex systems that you interact with might hold similar untapped potential? Think about software you use, processes at work, maybe even other technologies.
We're going to deep dive into the underlying controls or logic, reveal new ways to solve problems or improve things in your own world. Something to think about.